This is joint work with my advisor, Dimitri Simos, with my colleague, Stefan Zauner from FH Campus Vienna, and with our research collaborators, Rick Kuhn and Raghu Kakkar from NIST. At first, I will introduce the combinatorial structures that we use for fingerprinting, then a bit about TLF, then about the test cases we generated upon which we base our fingerprinting approach, our testing framework. Then we define the feature vectors that we use for classification. I present a case study where we evaluate our approach, and then we will have an evaluation both for different browsers and for different kind of sequences. In particular, we present an investigation on the applicability of combinatorial sequence testing methods to browser fingerprinting. We present an abstract model of the TLS handshake and a case study with 5 browsers demonstrating our approach. Browser fingerprinting is done for a variety of reasons, but in this work, we use a black box event testing approach. We use an abstract model of the TLS handshake, and our feature vectors are defined only in terms of the observed behavior of browsers during the handshake. Here in the figure, you see a TLS handshake. On the left side, we have the client, and on the right side, we have the server side. The handshake continues over the exchange of certain messages. And what we do in our paper is that we manipulate the right side, the server side, with the kind of messages that we respond to client requests. And this then, how the browsers react, will lead to a fingerprinting approach. We don't have to evaluate browsers against a single sequence. We can select multiple sequences upon to base the fingerprinting upon. We have then an execution framework which executes all the test sequences against all the browsers. On the result, we create feature vectors which we store in a database. And based on this, we can do classification. We formulated the following research question. Can the behavior observed from test sets created by sequence covering arrays containing TLS server-side messages be used to fingerprint browsers? Our approach has the following advantages. It can be used in conjunction with existing approaches. The behavior database can be computed and kept up to date independently of any specific target. And you cannot trust some properties that a browser reports to a server, like the user agent string. That's why we focus on classification based on observed behavior. A couple of years ago, the following testing problem was posed. It was suspected that the order in which peripherals were connected to a computing device could lead to errors. And this was the case. The mathematical formulation of the corresponding testing problem led to the definition of a sequence covering arrays, because a sequence covering array captures exactly the properties that are required for this testing. A sequence covering array of strength T with parameters n, s, and t is an n times s matrix where the entries arise from a finite set capital S of S symbols, such that every t-way permutation of symbols from S occurs in at least one row. The t symbols in this permutation do not have to appear adjacent next to each other, and each row is a permutation of the S symbols. This coverage criteria can also be expressed via the regular expression printed in the second box. Here you see an example of a sequence covering array of strengths 3 for 6 possible events. It has 10 test cases. Sequence covering arrays are based on a permutation model. This means every event occurs in every sequence exactly once, and all sequences have the same length. If necessary, you can artificially consider non-injective sequences, but in this work we use only permutations. We execute TLS handshakes, specifically TLS 1.2. In the handshake, the client connects to a server, and the semantics are encoded as an ordered exchange of messages. We modeled 6 server-side TLS handshake events: the server hello message, certificate, key server exchange, server hello done, change cipher spec, and finished. We use a tool called TLS Attacker. It was presented at CCS 2016. It is available as an open source framework, and it allows the creation of custom TLS message flows. And we use it to instantiate our abstract test sequences with its default values, to execute the events in the order that we specified them, and to save the response from the clients, and to this will then be annotated and stored in a database. From these 6 events, we considered all non-empty selections and then all permutations of them. And we stored all of these sequences in our database. This means, in particular, that we can find all sequence covering arrays for the respective parameters as a subset of the set of all these sequences. This led in total to 1,956 test cases. The test execution works as follows. First, you choose a test sequence. Then we created an XML translation of this test sequence to be input into TLS Attacker, which is started in server mode. Then we instrumented the browser to connect to a local resource where TLS Attacker was listening on. The framework will then respond with our defined message flow, and the handshake will continue until either the client aborts it or it is finished. And we record the message exchange and store an annotated version of it. To give a specific example, consider Firefox with the following sequence. First we send server hello, then finished, then server hello done, and change cipher spec. The result is that Firefox responded with a TLS alert message of type unexpected message, and additionally, from TLS Attacker, we obtain a Java exception. So the result database contains all test executions, all browsers against all sequences. And of course, this database can be pre-computed, it can be kept up to date, and it can be very easily extended. Now, for our feature vectors in terms of behavior. For given subset of sequences and browser, we take the result of executing the specific sequence against the browser, and then we combine all of these individual results in a bigger feature vector. So for all sequences, in our feature vector, we have a pointer to the individual array of results. To make this more concrete, here's an example. The top set has 2 sequences. The first sequence is just a singleton sequence of certificate, and the second sequence has 3 events. Now, the feature vector has 2 entries. The first is a pointer to an array which contains the first response, the alert message and of type unexpected message. And the second sequence leads to the response that is printed in the relation 6a to 6c. Now, for classification, for given non-empty set of sequences and 2 different browsers, we say that they exhibit different behavior with respect to S, if and only if their feature vectors differ. This then leads to an equivalence relation on the set of all browsers, which in turn leads to a partition on the set of all browsers. We say 2 browsers are equivalent if and only if their feature vectors are identical. And we can quantify the capabilities of the resulting distinguisher as a combination of the cardinality of the individual parts of the partition and the number of parts in a partition. Like I said before, we have 1,956 test sequences, individual test sequences. We took 5 browsers and we executed the test study on Windows in a virtualized Windows 10 environment. So for the evaluation, first we look at selections of 2 different browsers. Then we look at individual test sequences, and then we look at the combinatorial evaluation for sequence covering arrays. In general, we observed the following behavior. Microsoft Internet Explorer and Microsoft Edge for all test sequences had the same feature vectors. Also, Google Chrome and Opera had the same result. This is not surprising since they use very closely related libraries for their TLS implementation. And it follows that we will see the same behavior for any non-empty subset of sequences for these 2 browser pair selections. And this also means that the set of browsers has 5 elements. The resulting partition will always have at most 3 parts. And our current modeling cannot distinguish between these 2 browser selection pairs. Now, when we look at the individual sequences, we see always either 1, 2, or 3 parts in the partition. And for all of these numbers, we have at least 1 sequence where this number of parts occurs. We can make this statement more precise. We have 7 sequences where all browsers behave the same way. When there's 2 parts in the partition, we have seen two different partitions. So the first occurs 22 times out of 1,956. The first part contains Firefox, Chrome, and Opera, and the second part contains Internet Explorer and Edge. And the other possible partition which leads to 2 parts is composed as follows: a singleton Firefox and Internet Explorer, Edge, Chrome, and Opera together. And this partition occurs only once. When we have 3 parts in the resulting partition, the partition is actually unique and has the following 3 parts: a singleton Firefox, the second part is Chrome and Opera, and the third part is Internet Explorer and Edge. And this partition occurs 1,926 times. Now let's look at sequences of length 1. That means we just sent 1 sequence and 1 event. If we just respond with server hello, all 5 browsers behave the same way. When we send 1 event, which is either certificate, key exchange, server hello done, change cipher spec, or finished, as a sequence of length 1, we see the result is a uniform partition, but it has 2 parts. One class is Internet Explorer and Edge, and the second class is composed of Firefox, Chrome, and Opera. This means that even if we send just 1 event, we can, in some cases, distinguish some browser families. If we look at sequences of length at least 2 and sequence sets, which are sequence covering arrays, the result will always be the partition P3. That means we can reach the distinguishing with sequence covering arrays. So if we look at the results, we see that when we respond to a TLS handshake request, initial handshake request. If we respond with just one event, this has the weakest differentiation capabilities. This was to be expected. However, not even responding with just one event doesn't lead to complete uniform behavior of the considered browsers. If we select test sequences containing of at least 2 events, the resulting partition is equal to P3. And this occurs 98% of the times. And when we have test sequence selections of cardinality at least 2, this means we always have the best possible distinguishing that we reached. If we return to our research question, can the behavior observed from test sets created by sequence covering arrays containing TLS server-side messages be used to fingerprint browsers? We answer the research question affirmatively. Yes, combinatorial methods are applicable to the problem of fingerprinting browsers. We presented browser fingerprinting approach based on observed behavior. We used feature vectors based on the behavior and based on sequence covering arrays. And we established the applicability of combinatorial methods to the problem of fingerprinting browsers. Thank you very much.